The year is 1950. A British mathematician named Alan Turing publishes a paper asking a very simple yet incredibly profound question. Can machines think? He didn't have the hardware to prove it at the time. Computers were basically just giant calculators that took up entire rooms. But Turing conceptualized what we now call artificial intelligence, long before the term even existed. He proposed a test originally called the imitation game, but now known universally as the Turing test. The premise was straightforward. If a human evaluator conversing with both a machine and another human couldn't reliably tell which was which, the machine could be said to exhibit intelligent behavior. It was a philosophical stake in the ground, and it set the stage for what was to come. 6 years later, in the summer of 1956, a small group of researchers gathered at Dartmouth College. Organized by John McCarthy, this workshop was dedicated to the idea that every aspect of learning or any other feature of intelligence could, in principle, be so precisely described that a machine could be made to simulate it. This was the moment the field was officially born. It was McCarthy who coined the term artificial intelligence, as in also. They were incredibly optimistic. They thought they could solve the core problems of machine intelligence in a single summer. Of course, they didn't. But that optimism fueled the first wave of AI research. In the 1960s, we saw the creation of ELIZA at MIT, developed by Joseph Weizenbaum. ELIZA was essentially the first chatbot. It simulated a psychotherapist by using pattern matching and substitution methodology to give users the illusion of understanding. It was simple, but it was effective enough that some people genuinely believed they were talking to a real person. Then came Shaky the robot at Stanford. Shaky was the first general purpose mobile robot to be able to reason about its own actions. It could analyze in its environment, plan a route, and manipulate objects. These were significant early milestones, but the initial enthusiasm was about to hit a major roadblock. The reality of hardware limitations and the sheer complexity of human intelligence were starting to become apparent. The optimism of the 1950s and 60s eventually gave way to what we now call the first AI winter. In 1973, a critical report by Sir James Lighthill in the UK concluded that AI researchers had massively overpromised and underdelivered. The machines couldn't handle the combinatorial explosion of real-world problems. Funding dried up almost overnight. The hype had outpaced the technology, but the research didn't stop entirely. It just shifted focus. In the 1980s, we saw a brief resurgence with the rise of expert systems. Instead of trying to create a general human-like intelligence, researchers started building systems designed to capture the specific knowledge of human experts in narrow domains. Think medical diagnosis or chemical analysis. These systems use complex sets of if-then rules to deduce answers. For a while, they were a huge commercial success. Companies invested heavily, and it seemed like AI was back on track, but expert systems had a fatal flaw. They were brittle. They were incredibly difficult to update. They couldn't learn from their mistakes. And if they encountered a situation outside their programmed rules, they failed completely. By the late 1980s and early 1990s, the limitations of expert systems became too obvious to ignore. The cost of maintaining them outweighed their benefits. This led to the second AI winter. The term artificial intelligence almost became a dirty word in the tech industry. Yet, during this quiet period, the foundational work for the next revolution was being laid. Researchers were quietly working on artificial neural networks. These computational models, inspired by the human brain, were largely dismissed as impractical because they required too much computing power and data. But as Moore's law continued its relentless march, computing power was getting cheaper and faster. And the dawn of the internet was about to solve the data problem. While neural networks were quietly gestating, another approach to AI was making headlines. In 1997, IBM's Deep Blue, a highly specialized chess playing computer defeated the reigning world champion Garry Kasparov. It was a watershed moment. Deep Blue didn't use neural networks; it used brute force computational power, evaluating up to 200 million chess positions per second. It proved that machines could beat human first experts at complex strategic games, even if they were doing it through sheer calculation rather than human-like intuition. As we moved into the 2000s, the focus shifted towards practical applied AI. We saw the development of systems like Kismet at MIT, an early attempt at a social robot that could simulate and recognize human emotions. We also saw AI being deployed in the real world, quite literally out of this world. In 2004, NASA's Mars rovers, Spirit and Opportunity, utilized AI to navigate the Martian terrain autonomously, making real-time decisions without waiting for instructions from Earth. Then in 2011, IBM struck again. And this time, it wasn't chess, it was Jeopardy! Their new system was designed to process natural language. It was fed massive amounts of unstructured data from encyclopedias and the internet, and it successfully defeated the show's two greatest champions, Ken Jennings and Brad Rutter. Watson demonstrated that AI could understand complex, nuanced human language, complete with puns and wordplay. Around the same time, we started seeing the first mainstream consumer AI applications. Apple introduced Siri in 2011, and Amazon followed with Alexa in 2014. These virtual assistants brought natural language processing into our homes and our pockets. But behind the scenes, a much bigger shift was occurring. The hardware had finally caught up with the theory. Graphics processing units, or GPUs, originally designed for rendering video games, turned out to be perfectly suited for the massive parallel calculations required by neural networks. The stage was set for the deep learning revolution. September 30th, 2012. That is the day the deep learning revolution truly began. The event was the ImageNet Large-Scale Visual Recognition Challenge. ImageNet is a massive dataset of millions of labeled high-resolution images. For years, researchers had been trying to build software that could accurately identify what was in those images. The progress had been slow and incremental. Then came AlexNet. Designed by Geoffrey Hinton and his team at the University of Toronto, AlexNet was a convolutional neural network. It did just beat the competition. It absolutely crushed it, reducing the error rate by a staggering margin compared to the runner-up. This was the proof everyone had been waiting for. It proved that in deep neural networks, when trained on large data sets using powerful GPUs, could achieve unprecedented levels of accuracy in computer vision. It completely reshaped the AI strategy of major tech companies. Almost overnight, everyone pivoted to deep learning. The momentum was incredible. In 2016, a company acquired by Google called DeepMind took on the ancient Chinese board game Go. Go is exponentially more complex than chess. The number of possible board configurations is greater than the number of atoms in the observable universe. You cannot win at Go using the brute force calculation method that Deep Blue used for chess. It requires something akin to human intuition. DeepMind's system, AlphaGo, used deep neural networks trained on human expert games. And then it played against itself millions of times using reinforcement learning to improve. In a highly publicized match in Seoul, AlphaGo faced Lee Sedol, an 18-time world champion. AlphaGo won 4-1. It played moves that human experts described as beautiful and completely unexpected. It demonstrated that AI could master tasks requiring deep strategic thinking and intuition. We had conquered computer vision, and we had conquered the most complex board games. But the holy grail of AI research was still natural language, the ability to truly understand and generate human text. For a long time, dealing with natural language was incredibly difficult for AI. Traditional models read text sequentially, word by word. They struggled to understand the context of a word based on the words that came much earlier in a sentence. Then, in 2017, researchers at Google published a paper that changed everything. The paper was titled, "Attention is All You Need." It introduced a completely new deep learning architecture called the transformer. Instead of processing text sequentially, the transformer processes entire sentences or paragraphs at once. It uses a mechanism called self-attention to weigh the importance of different words in a sequence, regardless of how far apart they are. This means the model can understand context and nuance in a way that previous architectures simply couldn't. It was a massive breakthrough. The transformer architecture became the foundation for almost all modern natural language processing. It led directly to the development of large language models, or LLMs. Companies like Google developed BERT, and a research organization called OpenAI began working on a series of models called GPT. The first GPT model was impressive, but it was GPT-2 and especially GPT-3 that really started turning heads. These models were trained on vast amounts of text data from the internet. They could write essays, they could translate languages, and even write functional computer code, but they were still primarily research tools accessed via APIs by developers. They weren't accessible to the general public. That all changed in November 2022. OpenAI took their GPT 3.5 model, fine-tuned it for conversational interaction, and released it to the world as a free web interface. They called it ChatGPT, and it sparked a revolution. Within 2 months, it reached 100 million active users, making it the fastest growing consumer application in history. It wasn't just a technological milestone, it was a cultural phenomenon. Generative AI had finally arrived in the mainstream. The launch of ChatGPT fundamentally altered the trajectory of the tech industry. It kicked off an intense arms race among the biggest companies in the world. Microsoft, which had invested heavily in OpenAI, quickly integrated GPT-4 into its Bing search engine and its Office suite. Google, feeling the pressure, rushed to release its own conversational AI, BART, which later evolved into the Gemini models. Meta, Amazon, and a host of well-funded startups like Anthropic all accelerated their own AI programs. We moved rapidly from text generation to multimodal AI. Models could now understand and generate not just text, but images, audio, and video. Tools like Midjourney and DALL-E allowed anyone to create stunning photorealistic images from a simple text prompt. But as the capabilities of these models exploded, so did the debate surrounding them. The term AGI, artificial general intelligence, started appearing in mainstream headlines. AGI refers to a hypothetical AI system that can understand, learn, and apply intelligence across a wide range of tasks at a level equal to or better than a human being. A level of intelligence equal to or better than a human being across the board. For decades, AGI was considered science fiction, something that might happen in the year 2050 or beyond. But the rapid scaling of transformer models caused many experts to drastically shorten their timelines. Some researchers argue that simply scaling up these models, giving them more data and more compute, will inevitably lead to AGI. Others argue that large language models are essentially just sophisticated pattern matching engines, stochastic parrots that don't truly understand the world. They don't truly understand the world, and that a fundamental new breakthrough is required to reach AGI. This debate isn't just academic, it has profound implications for the future of work, the economy, and society as a whole. We are grappling with questions about copyright, bias, misinformation, and the potential for AI to automate vast swaths of human labor. We are standing at the precipice of a new era. The history of AI is no longer just a history of computer science, it is the history of our future. From Alan Turing's theoretical machine to the generative models of today, the pace of innovation is only accelerating. So we had the technology, we had the models, but what happens when you take those models and give them the ability to act autonomously in the world, to plan, to use tools, to take actions on your behalf? That is where the story gets really interesting. Let's talk about AI agents. The reality is the timeline for artificial general intelligence is the subject of intense debate among the brightest minds in the field. If you look at prediction markets like Metaculus, forecasters have dramatically pulled their estimates forward. Just a few years ago, the consensus was that AGI might arrive sometime in the 2040s or 2050s. Now, many are pointing to the late 2020s or early 2030s. Demis Hassabis, the CEO of Google DeepMind, the same team that built AlphaGo, has suggested that we could see AGI or something very close to it within the next decade. He argues that we are no longer constrained by algorithmic breakthroughs, but primarily by computational power and the availability of high-quality training data. This is the scaling hypothesis. The idea that if we just build bigger models, train them on more data, and run them on massive clusters of specialized hardware, emergent capabilities will continue to appear. We've already seen this happen. Models trained to predict the next word in a sentence suddenly demonstrated the ability to write code, solve logic puzzles, and translate languages without being explicitly programmed to do so. But there are significant bottlenecks ahead. We are rapidly exhausting the supply of human-generated text on the internet. To continue scaling, companies are exploring synthetic data, using AI models to generate training data for other AI models. There are also massive constraints regarding energy consumption and the physical manufacturing of semiconductor chips. Furthermore, critics argue that true AGI requires more than just processing text. It requires a grounded understanding of the physical world, causal reasoning, and the ability to learn continuously from interaction, rather than just from static data sets. Whether AGI arrives in 5 years or 50 years, the systems we have today are already powerful enough to reshape entire industries. The focus is shifting from purely theoretical research to practical deployment, safety, and governance. How do we align these powerful systems with human values? How do we ensure they are used responsibly? These are the questions that will define the next chapter in the history of artificial intelligence. To truly understand where we are going, we have to look at how these models are being integrated into the fabric of our daily lives. It's no longer just about chatbots in a web browser. AI is becoming the invisible layer powering the software we use every day. We are seeing the rise of AI agents, systems that don't just answer questions, but can take actions on our behalf. Imagine an AI that can not only draft an email, but can also access your calendar, schedule a meeting, book a flight, and organize your itinerary, all from a single prompt. This requires models to interact with external APIs, understand complex workflows, and recover from errors. This shift from conversational AI to agentic AI is arguably as significant as the transition from command line interfaces to graphical user interfaces. It changes the fundamental paradigm of human-computer interaction. We are moving from a world where we tell computers how to do something to a world where we tell them what we want done. This has massive implications for software development. The role of the programmer is evolving. Instead of writing every line of code manually, developers are increasingly acting as orchestrators, guiding AI models to generate boilerplate code, write tests, and debug complex issues. Tools like GitHub Copilot have already become indispensable for millions of developers worldwide. But this rapid integration also exposes the vulnerabilities of these systems. We've seen high-profile examples of AI models hallucinating, confidently presenting false information as fact. In a low-stakes conversation, a hallucination might be amusing. But if an AI agent is making medical diagnoses, reviewing legal contracts, or managing financial portfolios, the consequences of a hallucination can be catastrophic. This is why the field of AI alignment and safety has become the most critical area of research today. We have to figure out how to make these systems reliable, transparent, and robust. We need mechanisms to audit their decision-making processes and ensure they adhere to ethical guidelines. The technology is moving faster than the regulatory frameworks designed to govern it. Governments around the world are scrambling to draft legislation that balances innovation with public safety. The European Union's AI Act is a prime example, attempting to classify AI systems based on their risk level. The regulatory landscape is just one piece of the puzzle. The economic impact of AI is perhaps the most heavily debated topic of all. Historically, technological revolutions like the Industrial Revolution or the advent of the internet have ultimately created more jobs than they destroyed. They automated routine tasks, but they also spawned entirely new industries and professions that couldn't have been imagined previously. But many economists argue that the AI revolution is fundamentally different. Previous technologies automated physical labor or repetitive cognitive tasks. Generative AI, however, is beginning to automate creative and analytical work, the very tasks that were previously thought to be the exclusive domain of humans. We are already seeing the impact in fields like copywriting, graphic design, and basic software development. The cost of generating high quality content has plummeted to near zero. This is leading to a massive restructuring of the labor market. Some predict a future of widespread technological unemployment, where AI systems can perform almost any economically valuable task cheaper and faster than a human. This has led to renewed discussions about universal basic income and the need to fundamentally rethink our economic models. Others take a more optimistic view. They argue that AI will act as a powerful augmentative tool, a co-pilot for every profession. In this view, AI doesn't replace the doctor. It helps the doctor diagnose diseases more accurately. It doesn't replace the lawyer. It helps the lawyer analyze case law more efficiently. This perspective suggests that the most successful workers of the future won't be those who compete with AI, but those who learn to collaborate with it effectively. The premium will be on uniquely human skills, empathy, complex problem solving, strategic leadership, and the ability to ask the right questions. Regardless of which scenario plays out, the transition period will undoubtedly be disruptive. The speed at which these models are improving means that the half-life of many technical skills is shrinking rapidly. Continuous learning and adaptability will become the most critical survival skills in the modern economy. As we navigate the economic and regulatory challenges, we also have to confront the profound philosophical questions raised by artificial intelligence. If we eventually succeed in creating an artificial general intelligence, a system that can reason, learn, and adapt, as well as, or better than, a human, how do we define its status? This brings us back to Alan Turing's original question. Can machines think? We are building systems that can pass the Turing test with flying colors. They can hold nuanced conversations, write poetry, and express simulated emotions. But does simulating understanding equate to actual understanding? This is the debate around consciousness and sentience. Most experts agree that current large language models are not conscious. They are incredibly sophisticated statistical engines, predicting the next token based on vast amounts of training data. They don't have an internal subjective experience. There is no ghost in the machine. But as these models become more complex, as they are integrated with robotic bodies, and allowed to interact continuously with the physical world, the line between simulation and reality might begin to blur. If a system behaves in every observable way, as if it is conscious, does it matter if the underlying mechanism is biological neurons or silicon chips? These are not just abstract philosophical musings. They have real-world implications for how we treat these systems. If an AI system is deemed to have some level of sentience, does it have rights? Can it be held legally responsible for its actions? We are entering uncharted territory. For the entirety of human history, we have been the sole benchmark for advanced intelligence on this planet. We are now actively building our own successors. The history of AI is a testament to human ingenuity, our relentless drive to understand ourselves, by attempting to recreate our own cognitive processes. It is a story of incredible optimism, crushing winters, and staggering breakthroughs. And yet, despite all the progress we've made since that summer workshop at Dartmouth in 1956, it feels like we are only just at the beginning. The next decade will likely see more technological change than the previous century. The question is no longer whether machines can think. The question is what kind of world we will build with them. Thank you for joining me on this journey through the history of AI. If you enjoyed this deep dive, please hit the like button and subscribe to the channel. And for more insights into technology, Linux, and the open source world, be sure to sign up for the weekly newsletter at tondoslinux.com/subscribe.